Hello everyone, my name is Estefania Reyes Sepulveda. I'm originally from Colombia. I'm a biology major at Umass, Boston.
Hello, my name is Bobby. One of the classes that I took when I was a junior in college was Simulating Life. This is a 300 level biology class at my school.
I chose this course because I always like art, and I read the description that was kind of like a video game design for like biology majors. So I was like, oh, that's so cool. Like I'll be able to like play with art, and I'll be able to like do like little fun things, and also with biology because I'm really passionate about both things.
I was pretty excited, and it turned out to be, one of my favorite biology classes that I have taken at this school. It was fun to work with the other students and see their projects. It was fun to just have my own idea and take in my own directions and basically test what I wanted to test. And it was also fun just creating and being an expert on your own simulation and your own, basically biological world that you've created. So I think all of those kind of make that class special for me.
Hello, my name is Brian White. I'm a biology professor at the University of Massachusetts, Boston. I teach a variety of courses at the upper and lower undergraduate levels, and my research is in biology education. I'd like to talk to you today a little bit about a class, an upper level biology class called Simulating Life, that I've developed over several years, and it's been extremely successful. I didn't want to make programming be a prerequisite for this course. I wanted to be so biology majors could take it whether they'd had programming or not. And also many biology majors are sort of programming phobic, and so I wanted to create a course for students who hadn't taken any programming classes. And what I discovered is there's a programming language developed by some folks at MIT called StarLogo Nova, which I'll show in a few minutes, is a drag and drop programming language, which you just plug blocks together, and you can quite rapidly code up things that already have pieces moving around and interacting. So it has a very shallow learning curve, and it gives students very positive feedback. Quite quickly they are able to develop very interesting simulation. So you have a collection of different kinds of agents, several or hundreds of each, and each one has their individual behavior that you code, and then you see how they behave. And those agents, for example, could be predator and prey, they could be enzyme and substrate, they could be immune cells and infecting bacteria, they can be all a host of things, even chemical molecules of a variety of sorts. And the idea is that you set up the rules of the game, and then you observe how the game gets played by all of those various agents. And the challenge all along the way is to make sure that your agents are behaving in a biologically reasonable way. For example, predators can hunt, they can see their prey, but enzymes can't see, so they can't hunt their substrates, and that you have to bear all of those sorts of issues in mind when you're doing your coding. So this course is both for my students and myself one of the most fun courses I have to teach and that they ever take. Because they get to develop their own simulation based on their own ideas, they put an enormous amount of work into these simulations and end up learning things that they never would have imagined. Students have learned rather sophisticated statistics in order to test hypotheses that they certainly would not have without the class to motivate them. In addition, because we create a community in the class where they help each other, where some students will develop expertise in one kind of programming and help others. And even more, it acts as a capstone because students you might see the similarities between predator and prey and enzyme and substrate and immune cell and pathogen, and see what's similar between them and what's different between them. And it really is amazing to see how proud they are of their work, but also how far they've come. That if you'd shown them their simulations in the beginning of the semester, they would never have believed that they could create these things. But the tool is so simple to use and gives you such rapid feedback as you develop the software that the students are able to do quite remarkable things. And my job as the professor is to guide them and help them see how to program, but also to continually move the goalposts. That is, once they've got it working in one way, can they add a feature? Can they do a little bit more? Can they do comparisons? And by the end of the semester, not only have I led them to create their own simulations, but also to collect data and test hypotheses with their simulations. And an added benefit also of the class is that what happens is students do simulations of a wide range of things. I found this class to be extremely useful, and I also think that it's extremely portable. That is, it doesn't require particularly specialized technology, and the software is free. And so I encourage people at other universities to try this out, because I think it's quite likely to be enormously rewarding both for the students and for the professor. And if you have questions, you can always contact me at my email below.
Today I'm going to show you my simulation. So the aim of my project was to simulate the rate of speed at which macrophages are able to move to fight off an infection. In the screen, you can see the purple thing represents the wound. The pink area represents the skin. The red area represents the blood. The pink circles represent the B cells, and the B cells, they create antibodies every once in a while and when they move around. The white circles represent the antibodies, and the small little green squares are the macrophages. For my simulation, we are also able to see as time goes on, the wound will begin to release bacteria, and there's two kinds of bacteria. There is the black bacteria that's called the normal bacteria, and there is a bacteria that has not been touched neither by macrophages nor antibodies, so it remains black. And there is the blue bacteria that has been touched by or has encountered an antibody or a macrophage. And every single time a macrophage eats up or eliminates bacteria, it will release a yellow stain, and the yellow stain will indicate the macrophages to move slowly. So now I'm going to play my simulation. So now you're able to see how the black bacteria and the blue bacteria are coming out of the wound. And as macrophages eat up the bacteria, they leave a yellow mark, a yellow stain that the interaction, the fighting up the infection has already occurred. And for this, my hypothesis was that macrophages moving slowly in the yellow stain are able to eat more bacteria, and since they'll be concentrated in that place, the infection will get rid of quickly. But although my simulation did not support my hypothesis at the end, because I tried this also without the yellow stain, it did allow me to conclude that for this model, the speed at which macrophages move affects the ability for them to fight off a bacterial infection. And further research could be done on how the response of the macrophages will be if the bacteria will reach the bloodstream. As you can see in this part right here, we have a different interaction after the bacteria has reached the blood. And overall, the simulation was able to test effectively the behavior of macrophages when they come in contact with bacteria and how the immune system was able to respond.
Suppose we wanted to model this enzymatic pathway, that we have 3 substrates and 2 enzymes. The red substrate molecule reacts with the square enzyme to become purple. The purple substrate molecule reacts with the triangle enzyme to become blue. Suppose we wanted to model this in Star Logo Nova, it would be relatively straightforward. And here's what it would look like. So here, if we scroll up, the top part of the window shows where the action will happen. This big green area is called Spaceland, where the agents will do their work. Here's a graph to show the results. And most simulations have 2 buttons, a setup button that creates your agents and a forever button where they run. And so let me show you some of the code. So for example, in the setup button, what we do is we set the clock to 0, clear the line graph, create 100 molecules, and we're going to start with red ones, create 10 of each kind of enzyme, and get them ready in the world. And there's other code here about graphing, which we won't talk about much now. Once we've created them, when we press forever, we want them to move. And all of them, enzymes and molecules, should move the same. Each time tick, they take a step forward, and they do a little random turning, so they kind of meander. The main part of the code is here in the molecule panel. So when a molecule collides with an enzyme, you want it to do the right thing. So if I'm a red molecule and the shape of the collidee, the thing that I hit, the enzyme that I hit, is a cube. So if I'm red and hit a cube, I turn purple. And here's how we could code the next set of steps in the pathway. So for example, here I could say if my color is purple, that is the next stage of the pathway. If my color is purple, and we'll need another logic block here, and the shape, I'll go back to traits, and the shape of the calliope, we'll come get that block in a second. There's a built-in shape cube. We'll have to remember to come back and do that, the triangle. So if I hit the second enzyme in the series, then I want to set my color to to the final thing, to color blue. My color to color blue. And then let's go and grab that calliope block. So now this top code models the first step in the pathway. If a red molecule substrate hits a cube enzyme, it becomes purple. If, on the other hand, a purple substrate, purple molecule hits a triangle enzyme, it becomes blue. So that's the second step of the pathway. So now we can run it and see. So run code effectively compiles it. If we set up, and we now see our world with our starting number of red molecules and square and triangle enzymes. As you can see, some were born having collided and have already turned from red to purple. And we can then now hit forever, and you can see the molecules move around. As if you watch, you see enzymes colliding and the color changing now. So the red now to purple, and eventually we should start to see some blue. And if we want to make this go faster, we can speed it up. And so what you can see, if you run it for long enough, the red decreases. And then you get a sort of steady state purple, the middle step in the pathway, until basically the very end, everything runs out. And so you can watch the trends over time, over the course of this reaction. And of course, you could model all sorts of other things, but this gives you a general sense of how simple the coding is, that you just plug in blocks and they drop into the proper place and they won't fit in the improper place. And how easy it is to change things and to modify them, and you get a graph. And this simulation took for only a few minutes to put together and is now fully functional. And you can do a variety of experiments. You could change the levels of the enzyme, you could change the amount of substrate, you could change the probability of collisions. A whole variety of things could now be built on from this.
Thank you.
Thank you for your time.